Hi, my name is Vincent, and today I'm going to talk about the lab number 4, which is oscillations. I'm from physics class of 2211. In this presentation, I'm going to give a brief introduction about the purpose of this lab and the models and fundamental principles and a brief preview of the main results of the lab. And I'll talk about the details of the code and how the principles are presented. And I'll give a comparison between like the experimental and the computational model. Then later on, I'll answer some further questions. So the purpose of this lab is to find the motion of the spring mass system with the mass oscillating in an arc. So I will use the tracker first to observe the experimental of the observed position, and later I'll use glow script as a computational model to compare the graph's motion and energy, and to see whether the delta system's energy remains at zero, and whether it demonstrates the energy principle. So the physics main principle in this presentation is the Newton's second law and the energy principle using the system of mass, spring, and the earth. So in the result, like the brief result, like the system's total energy do follow and demonstrate the energy principle as the delta E is approximately zero. So yeah, I'm going to talk about this Newton's second law, like the system's delta momentum proportional of time to net force applied, or F net equals to delta P over delta T. And you can say that F net is equal to the force of spring plus the force of um, gravity will equals to like the equations on your right hand, and the energy principle. So in this system, I use the mass, the spring in the earth, and there are no surroundings. So the change in kinetic energies plus the change in potential of spring energy and the change in gravitational potential energy is equal to zero. So I have used the tracker to track all of my like motions of the experimental, and then like to calculate the oscillations, I use t equals to 2 pi square of m over k, and that is why I can find the k equals to 4 pi over 2 multiplied by m over t squared. So the initial conditions, I'll give the ball position is the vectors of minus 0.1 and about minus 0.6, and then the k like the spring constant is 6.872, as I have showed you the equations in the previous slide, and the relaxed length of spring is about like 0.126. And then I'm gonna change like the potential gravitational energy is equals to mj delta y delta the change in height, and the potential energy in spring equals to 1/2 k multiplied by delta s square. And you can see that like the spring, I can calculate the velocity after all using the updated velocity equations in the Newton's second law, and then I can use it and update the position equals to delta s equals to v multiplied by delta t, and on your right hand is the data of my slides. So in overall, you can see that the experimentals and the models are not that like they don't have a high discrepancy and don't have a high like difference. There are possible errors that may lead to a very small discrepancy, which is maybe human errors, like I have like inaccuracy in identifying mass, or maybe numerical errors, or maybe the theory are not always accurate. There can be work surroundings, and still the energy principle is still satisfied as there are no external force affect isolated system, and the change in delta E is equal to zero. As you can see, the orange line is still at zero over all the time. So the what if questions, like I have put the graph of the x direction and the y direction, and then from like seconds of 4.1 to 5.7, the oscillations is about like 1.5 seconds, and I can calculate the spring constant is about 6.8 in the x direction and 6.05 or 4 in y direction. This difference and this discrepancy can be affected by the spring in the x direction and the y direction. so there can be a little big difference when it gets to the x and the y direction in the spring. So that's all for today's lab. I hope you have a nice day. My name is Vincent, and I hope to see you guys later in